to the Hillside Club on this rainy evening, February 1st, 2021. It is my pleasure to welcome you all here to our Fireside series at the club. This is a series of presentations which has a century-long tradition of these meetings, community sessions, gatherings, hearing from members of our community on first Mondays. They've continued even during times of war, when our country was being besieged in various ways, including by a pandemic. We continue to forge this community, and we're so grateful to have you all here joining us this evening. This club is now 122 years old and was formed by a group of women. We would now call them environmentalists, though that term didn't exist then, who were determined to shape in a positive way the development of the Berkeley Hills. And we respect their legacy and continue it by these talks as one part of that. And I'm so pleased tonight to be able to share with you a topic that is the overarching theme of our year, which is providing messages of hope. During a time when we're all struggling and facing unusual challenges, still there are messages of hope. And tonight we are hearing about probably the most common topic in the news right now, which is about the pandemic and especially about vaccines. So just share with you briefly, back in the spring of last year, in April, I tuned into a presentation by university experts, and I was delighted to see my client there, Dr. Lee Riley. And then I got the idea that I would like to include him in this series. But all last year, it seemed like the wrong time. We wanted to wait until we really could be talking with a light at the end of the tunnel and some hopefulness. And this seems like a very appropriate time. This week, especially, the Sunday comics started with a Doonesbury strip talking about vaccine envy. So this is absolutely the topic on everyone's mind. So it is with tremendous pleasure that I welcome to the Hillside Club, Dr. Lee Riley.
Thank you, Arlene. That's a very nice introduction. And I'm really honored to be invited to this session today. Okay. And so I'll just go ahead and start. I'm going to talk maybe for about 20 minutes or so, just some background about COVID-19, some of the common questions that people have asked, some of the questions that people like me, scientists, have asked, and we try to answer some of those. Of course, we don't have answers to all of these questions. And then I'll just open up for questions. And
well, actually, let me just mention what we will do is, in fact, instead of opening up the mics, if you do have questions, I would say first listen to Lee's presentation because he may very well answer some of them. I do have a number of questions that people have put to us in advance, but put your questions in the chat. Between Jim and I, we'll be trying to catch as many of those as possible. We already have experienced a little bit of lag just from, I'm here at the club in front of the Fireside, Jim is in the green room, and we already have enough with the two of us to get lag. So if you could be kind enough to put your questions in the chat, and then we'll get to as many of those as we possibly can. So with that, Lee, why don't you take it away?
Okay. So Jim, can I have the screen sharing capability here? Okay. Can everyone see this? Okay. So this is the title, what has science learned and what does it still not know? And so when the pandemic began, as everybody knows, in China, sometime in December in 2019, and we started talking about this in late January here in this country. And so, sometime in the middle of March, I was asked to give a talk about what we knew about this disease at that point. And so, this was a lecture to a group of Masters in Public Health students at Cal. And so these are some of the questions that we all had at that time. So the first question was, where did this virus come from? And then when did it enter the United States? And what explains the regional differences in mortality? And why is it so transmissible? And then can a vaccine be made against this virus? And so when we were asking those questions, this was the situation with this pandemic at that time. So there were about 11,000, almost 12,000 confirmed cases worldwide with 450 deaths. In the US, there were only like 250 cases, 50 cases. And so the epicenter at that time was Europe, almost 10,000 cases. In Africa, there were only 37 cases reported, confirmed. And this is what what we call the epidemiology curve looked like. I don't know if you can see, but you can see there's the red bars down here are all the cases in China. And then the epidemic began to really spread. And today, just 2 days ago, this was the situation. So as of January 30th, there were more than 101 million cases confirmed worldwide, with more than 2 million deaths. And so these, as the pandemic evolved, many new questions were asked, such as what proportion of exposed individuals get asymptomatically infected? And then what's the mortality rate from COVID-19? And what's the hospitalization rate? Does the mask prevent transmission? Can you get the virus from virus-contaminated inanimate objects? Does the lockdown work? Does the virus mutate? What's the mechanism of respiratory failure preceding death? And why are severe clinical outcomes with COVID-19 less common in children? And how effective are the authorized vaccines? And some of these vaccines got developed and authorized for use in less than 1 year. So how safe are these vaccines? And finally, the question that everybody's asking right here, right? When will the pandemic end? So just quickly, where the virus come from? Where did the virus come from? So coronavirus. So as you know, the virus that causes COVID-19 is a member of the so-called coronaviruses, and there are actually three main groups of coronaviruses. And so group one includes 229E and NL63, which cause the common cold that we all have. And then also other upper respiratory infection causing viruses in group two, but the so-called pandemic prone viruses, the kind of virus that we're talking about, the SARS-CoV-2, belong also to group two. And just if you do phylogenetic analysis of the genome sequences of these viruses, you can see in the red, these are all of the pandemic prone, these are the SARS-CoV-2, the current coronavirus. And they're somewhat distantly related to the first SARS coronavirus that we heard about. This was back in 2003 when we had a pandemic of another coronavirus, this SARS-CoV. Sometimes called CoV-1 now. And that epidemic, as some of you probably remember, just disappeared after about 6 months. We don't know why, but it just disappeared after 6 months. So that virus was actually distantly related to the current coronavirus. And then if you do these sequence analysis to other types of viruses, it actually turns out the current coronavirus is very closely related to a virus from a bat. But some parts of the genome, the sequence, is actually more closely related to a coronavirus that was isolated from pangolins. So at this point, we don't know if the pangolins were the immediate source of the human coronavirus, or if it's the bats, or some other intermediate animal source. But it clearly came from some animal source that the humans came in contact with. Now, I should also mention that the common cold coronaviruses that we get infected with probably entered the human population about 200 years ago. And they're believed to be closely related to cows. So it's possible that when that coronavirus, the common cold coronavirus, entered the human population, it may have caused a similar type of pandemic. And over the years, the virus attenuated itself. Well, let's just hope that this coronavirus, the SARS-CoV-2, doesn't take 200 years for it to attenuate itself. When did it enter the U.S.? There's a New England Journal of Medicine paper that came out that describes the first case of coronavirus infection, and that happened in January 2020. There's some controversy about this. There's some people claim that the first case occurred here in California in Santa Clara County. And what explains the regional differences in mortality? We don't really know. So here's the situation. So I looked at the case fatality rates back in June of 2020. And so at that time, when the epicenter was in Europe, 15% of the people who got infected died in France. In the UK, it was 14%. In Italy, it was 14%. And in Spain, it was 10%. But for some reason, in Germany, at the same time, it was only 4.7%. So why is this difference? And then if you look at the US, New York, and it was particularly New York City, the highest case fatality rate at almost 8%, Connecticut, 7.1%, New Jersey was 6.9%, Illinois was 4.4%, but California was 3.4% at that time. And then if you look at California itself, if you look at Santa Clara County, it was 5.1%, Los Angeles, 4.3%, in San Diego, 4%, but the Bay Area, San Francisco, it was only 1.6%. So why do you think there's this regional difference in case fatality rates? And so we looked into some of the suggested reasons. So we looked at things like the timing of the lockdown, the initiation of the lockdown, and the median age of the population, and underlying comorbidities, underlying medical problems such as diabetes and hypertension, and hospital beds, and number of tests done per 1 million people. And if you look at this in Europe, you can see that Germans actually had the highest mean age. So it's not the mean age. When the epidemic first hit Italy, people were saying that Italians have the highest median age, but it's actually Germany that has the highest median age in Europe. And the lockdown didn't start in Germany until after some of the other countries had started. So that's not the reason. If you look at the number of beds per 1,000 population, yes, Germany does have more beds than others, but I'm not sure if that's the reason. And then in terms of the number of tests, that doesn't seem to correlate. If you look at the US and the different states, so California had the lowest case fatality rate. And again, it is true that California started the lockdown first of all the states, and in particular the Bay Area. But if you look at things like median age, yes, California actually has the lowest median age, so that might be contributing that. But I don't think that's the reason, because I just told you that in Germany that wasn't correlated. Comorbidities, again, we don't see a pattern. Number of hospital beds per 1,000 population. California actually has the lowest number of hospital beds per 1,000 population, and so we couldn't really see any correlation with any of these factors. And then when you look at the counties in California, again, there's really no correlation with any of these parameters. So we don't really have a good explanation why case fatality rates vary. Why is it so transmissible? We have no idea. Although we do have some suggestions. And so this is something that we do in my lab, where we track the different types of variants of the virus. And everyone's talking about variants right now, but these variants have already existed ever since the epidemic started, and they come and go. So if you look at these different variants, if you look at the variants in Northern California and Southern California, they actually do differ. And that could potentially explain why the rates are so much higher in Southern California. But Again, that's really speculative. But we really don't have a good idea why it's so transmissible compared to, for instance, some of the other coronavirus that we've seen in the past. And then, can a vaccine be made against this virus? Yes. So we're going to talk about that later on. And so these are some of the vaccines that you've been hearing about, the so-called messenger RNA vaccine. Two have already undergone emergency use authorization, the one from Moderna and Pfizer. All of these vaccines are based on the so-called spike protein of this virus. Spike protein is the protein that sort of juts out of the viral body, virus particle, and it facilitates the attachment of the virus to the receptor on the human cells. And the receptor is called ACE2 receptor. And so that was the idea. So if you can if you can raise an antibody against that spike protein, that will block the spike protein from attaching to the cells, so you don't get infected. There are also so-called virus vectored vaccines, and that's a good example of this is the one that you've been hearing about recently, Johnson & Johnson vaccine. Here, what they do is they express this coronavirus spike protein in another virus. It's called adenovirus. Adenovirus is usually it's completely harmless to people. It may cause cold-like symptoms, but this particular adenovirus, adenovirus 26, doesn't infect. It's not very common among human population, except in certain places in Africa. And so AstraZeneca made a similar type of vaccine, that virus vector vaccine, and they use a chimpanzee adenovirus, which doesn't infect humans. And then Sinobiologicals, they use adenovirus, right? There's a Chinese vaccine. And the Russian vaccine used the same virus as the Johnson & Johnson vaccine. Early on, everybody was criticizing the Russian vaccine, when in reality, it's really no different from the Johnson & Johnson vaccine approach. Okay, I think that people criticized the Russian vaccine when they went ahead and rolled it out without really large-scale trials. But in retrospect, it probably was not a bad idea that they went ahead and released it early. And then there's the inactivated SARS-CoV-2, where they actually formalin kill the virus. And this is something that the Chinese have done in some of their vaccines. And then there's also the recombinant subunit protein vaccine, where they actually purify the spike protein. So they express the spike protein in the insect cell, okay, and then purify it, and then use that as a vaccine. So one example of this, which I think is going to probably undergo EUA in the next couple of months, is the one from Novavax. And so other questions: what proportion of exposed individuals get asymptomatically infected? 30 to 40%. What's the mortality rate from COVID-19? Hospitalization rate? Depends. Early on, as I indicated to you, their mortality was quite high, but as people learn to manage these severe cases, the mortality has really gone down. Okay, so we learned in the process of how to take care of severe cases, such as using dexamethasone, as you heard about, and then these monoclonal antibodies. And so we're much better at taking care of these patients now than at the beginning of the pandemic. And so the overall mortality, depending on where you are, is anywhere from 1 to 1.5%. So it's dramatically come down. Does the mask prevent transmission? Yes. And can you get the virus from virus-contaminated inanimate objects? It's rare. It really depends on the type of the object. Some viruses would disappear, get killed very quickly in certain types of surfaces. Some type of inanimate object may linger a little while longer. But no matter what, this kind of transmission is extremely rare. I know people go crazy, washing their vegetables and fruits and all this, and they're probably not necessary. That's probably an overkill. Does the lockdown work? Yes. And does the virus mutate? Yes. And the virus is mutating much faster than first thought. And what's the mechanism of respiratory failure preceding death? We don't know. There are a lot of ideas, but they're all conjectures so far. And why are severe clinical outcomes of COVID-19 less common in children? The answer to this question, answer to the first question may answer this question. So we need to know the mechanism of respiratory failure. If we know that, then we can also figure out why the severe disease doesn't really happen in little kids, except for this one syndrome called a multi-system inflammatory syndrome, which happens in some kids, but it's not that common. And how effective are the authorized vaccines? So here's the whole story. So with the messenger RNA vaccines, the Moderna and the Pfizer, they're anywhere from 94 to 95% effective. With the Johnson & Johnson vaccine, when the trial was done in the US population, it was about 72% effective. But in South Africa, it was 57% effective. And part of that is probably because of this variant that you may have been hearing about that's really exploding in South Africa. And then the Novavax vaccine, again, the same thing. In the US, it was 90% effective, but in South Africa, it was only 50% effective. So some of the vaccines got developed and authorized for use in less than 1 year. How safe are these vaccines? So the messenger RNA vaccines are quite safe. They are associated with certain type of side effects, such as pain and swelling and redness at the site of injection, and then systemic symptoms such as fever, fatigue, headache. These are more common after the second dose. Many of you probably already got the vaccine, probably the second dose, I assume. So you probably know this. So yeah, my wife got her second dose last Monday, and she had fever and chills even, and it was kind of not completely debilitated, but she wasn't herself for about the next 24 to 48 hours. But there have been some severe adverse events reported, and you may have heard about this, the anaphylaxis reaction. It's really rare. The most recent data from the Pfizer, all the people who received the Pfizer vaccine, this reaction is about anywhere from, it's around about 5 per million doses. With the Moderna, it's slightly less, anywhere from 2.5 to 2.8 per million doses. And so those are compared to what we see with the influenza vaccine, which is 1 to 1.3 cases per million doses. And so, there's this idea, there's this kind of a perception out in the media, in the community, that these vaccines got developed and authorized for use in less than 1 year. And this is actually incorrect. I want to really correct this misconception. The science behind messenger RNA goes back almost 30 years. And I would say there are two people who are responsible for why we now have this amazing, highly effective vaccine. One is Katalin Karikó. She's an immigrant from Hungary. She came to this country and became a scientist at the University of Pennsylvania. And she's the first one who came up with this idea that if you put messenger RNA into a cell, you can produce proteins. And for many, many years, she tried to convince her colleagues and people at the University of Pennsylvania. Nobody paid attention to her. They ignored her. She couldn't get any grants. She couldn't get promoted, but she persisted. And about 15 years later, she figured out that if you make, so messenger RNAs are usually made synthetically, okay? And or you can try to purify them for the virus. But if you do that, try to purify the messenger RNA from the virus or the make a synthetic RNA, they end up with some contaminants. And these contaminants are double-stranded messenger RNA. Remember the RNA and DNA? DNA is usually double-stranded. Messenger RNAs normally is single-stranded. But when you make these synthetically, you get these double-stranded contaminants. And they're the ones that actually trigger an inflammatory response in these cells. So these cells, when the messenger RNA goes into cells, the cells recognize that some foreign product got into the cell. So it induces this inflammation. And so she just could not prevent this inflammatory response from happening. And that's what prevented this idea from really taking off. But then she figured out how to remove those double-stranded RNA by HPLC, which is a type of chromatography, separation. And when she did that, that the inflammatory response severely decreased. But then there was something else that needed to be done. And then came Dr. Drew Weissman, who's at the University of Pennsylvania as an immunologist. And he and Kathleen Carico worked together. And they figured out that if you change some of the nucleosides, then you can completely reduce the inflammation. And so that was so these two really contributed to the eventual use of the messenger RNA as a type of vaccine. And then there was also Ugur Sahin, who's from Turkey, and he immigrated to Germany. And he heard about this idea. They published their papers about 15 years ago. And he heard about this idea, and he really thought this would be very useful for cancer therapy. And he's the one who went on to start the BioNTech company, which you now heard about. And then some other people here in the US, there's a postdoc at Stanford who read Dr. Carico's paper. And he thought this was an amazing idea. And he started using this for immunotherapy. He started thinking about using this for immunotherapy purposes. And then he started talking to a group of bioengineers in Boston, who then thought that this is a great idea for a vaccine. And this person, Langer, who suggested that the idea of using this as a vaccine, went on to start Moderna. Okay, and so this is how the story evolved. So there would be no such thing as Moderna if it weren't for this immigrant, Dr. Carico from Hungary. Okay, and thank goodness we have this visa program in the US called the H-1 visa, because if it weren't for the H-1 visa, which the last administration tried to eliminate, we would not have this vaccine today. And it was Dr. Sahin who heard about the work of Dr. Carico. And if it weren't for the immigration policy in Germany at the time he immigrated to Germany, BioNTech would not exist, and the Pfizer vaccine would not exist. So these two immigrants have made major contributions to why we have these vaccines right now. And it's an extremely safe vaccine. And the reason for this is because, and this is something that even when this first came out, I was concerned as a physician. I asked myself, okay, this is an RNA, it's a nucleic acid. Is it not going to go into the nucleus of the cell and somehow end up incorporated into the chromosomal DNA, and then sort of cause all these mutations? Well, that doesn't happen because messenger RNA never goes into the nucleus. Messenger RNA, pure messenger RNA, goes into the cytoplasm, okay? And then they get translated into amino acids and then into proteins. And then the proteins get expressed on the surface of the cell. So these are antigens. They're presented on the surface of the cells. And these antigens are recognized by the immune cells. And the immune cells, when they're stimulated, then start undergoing this cascade, ultimately making the antibody against this antigen. So in a way, the protein that's produced by these cells is sort of like the Novavax protein. And then in Novavax, as I mentioned, they use the insect cells to make the protein, and then you inject the proteins as a vaccine. Here, your own muscle cells make the same protein. So your cells does the work for you, and you don't need to purify it. And the RNA is synthetically made. It doesn't even come close to any infectious agents. So it's all synthetic, okay? And there's no chance that it can incorporate into the nucleus. So after I learned all this, I was completely convinced that it's one of the safest ways to make a vaccine. And about a couple of weeks ago, I was asked by a physician friend of mine in Oakland, who works for this community-based clinic called Roots. There's a number of physicians and nurses who work there, and they were somewhat concerned. They're healthcare providers, so they have some knowledge about how vaccines work, and they knew enough about vaccines to actually be worried that this may have some consequences. So I talked to them about what I learned myself, and after talking to them, they were all convinced that this is safe. They all went ahead and got their vaccines, like within a couple of days after I talked to them. And so, so that's the story of the messenger RNA vaccine. Okay. And so the last question, when will the pandemic end? So here's, I don't know if you saw this, this is a New York Times article that came out a couple of days ago. And this situation back in January in Wuhan, China, 2020, January 2020. And this is Wuhan now. Okay, this is what's been happening with this pandemic in the United States until a couple of weeks ago. And this is what's been happening with this pandemic in China. Pandemic is controlled in China. Okay, pandemic is ended in China, but not here in the US and many other parts of the world. And I can tell you, a huge proportion of this pandemic is largely driven by humans and politicians and those people who don't believe that this pandemic exists. They're the ones who are really fueling this epidemic. And of course, I'm exaggerating. US was totally unprepared. We didn't have the public health infrastructure that's needed to really mitigate this pandemic from the way it's taken off. We didn't have the testing facilities. CDC's hands were tied because of the administration. FDA's hands were tied. And so all these, it was just like a perfect storm. And this virus just took advantage of all the human failures to just take off in the way it did. So what will happen to this virus? So will it behave like the first SARS coronavirus that happened in 2003, just disappear after 6 months? Or will it behave like the Middle Eastern severe respiratory syndrome coronavirus, which right now is still continuing, but it's pretty much confined to the Middle East? And the reason for this is because the reservoir of this virus is the camel. So it's an occupational hazard, and it really hasn't taken off in the way the COVID-2 has. Will it behave like the influenza virus, where every year we have a new strain coming out and we need to come up with a new vaccine for it? This is so-called a seasonal influenza. Or will it behave like the common cold virus? It becomes endemic and ultimately attenuate itself. As I mentioned, it took 200 years for this the common cold coronavirus to perhaps attenuate itself. We don't really know. But we do have these vaccines. They're effective. There's some concern about the variants that are emerging, that the vaccine may not be as effective. But because of the technology of the messenger RNA vaccine, they can easily come up with a new messenger RNA vaccine. In fact, the Moderna, Pfizer probably already has these vaccines. The concern is not so much developing the new vaccine, but all of the regulatory process that these vaccines may need to undergo. We hope that they don't have to go another year of testing for these new messenger RNA vaccines to be rolled out against these new variants. But this is something that's a decision that needs to be made by the FDA. But the more of the concern is, okay, so let's say we're able to control COVID-19 completely. Will there be COVID-21? Will there be COVID-22? Will there be COVID-23? And what about COVID-24? And why am I worried about COVID-24? Well, 2024 is the next presidential election, right? And there is a concern that the previous president might come back. And if that happens, I think we probably shouldn't leave this planet, because this will definitely be an unsafe place to live. So I'll end here.
Thank you, Lee. An interesting place to end. I can't help but talk about the correlation between the reaction to the pandemic and the reaction to climate change. As you said, humans are responsible for it, and there are a lot of people who are claiming that it isn't really happening. So very close parallel. So I hope we're doing more and more quickly in solving the pandemic than we have with climate change, for sure. So we have a number of questions. I'm going to divide them into pre-vaccine questions, vaccine, and post-vaccine questions.
Mhm, mhm.
So a couple of pre-vaccine questions. A basic one about while we're still wearing masks, are double masks useful, or masks with filters significantly more useful than just a normal mask?
Well, certainly double masks or masks with the filters would be more protective, but I'm not sure if they're necessary. I'm not sure how much more will these double masks or filtered masks contribute in interrupting the transmission. You know, if you don't feel uncomfortable wearing them, sure, you can wear them. But just any ordinary masks will prevent most of the transmissions. And so, if you are really concerned, that's probably something that you could do. But they're not really going to be. It would be an incremental protection. Okay.
Understood.
Mhm.
Also, in terms of social distancing, originally we were told 6 feet. Then there was some talk about that maybe that really wasn't adequate. What is your sense of what is an appropriate distance
So
pre-vaccination?
right. So that really depends on sort of the context of the interaction that you may have. Closed space with no air circulation. Perhaps you may need to be further apart, but again, this 6 foot distance rule really is based on the influenza transmission, and so a lot of studies have been done with influenza, and that's what they came up with. So they're extrapolating that to the COVID virus. But there are many other factors you need to consider. So, that's generally a good rule to follow. Mhm.
Moving into questions about the vaccines themselves, you pointed out now there are a number of them both in the works and two that are available at this point. Should we as consumers be particularly concerned about which vaccine it is that is being offered to us?
So, I think you should go ahead and get the vaccine. If you have an opportunity to get any of these vaccines, you should go ahead and get them. Um, there are advantages and disadvantages of each of these. As I mentioned the messenger RNA vaccine, they both require 2 doses. And so you need to go back. You need to sort of time it in the way that you can get the second dose. Um, and then the Pfizer vaccine requires a super cold temperature for maintenance, so they're more difficult to administer. So that's more of a problem of the healthcare providers who have to administer the vaccine. They have to be really careful in handling it, um, making sure that they don't break the cold chain. But as far as the people are concerned, it really doesn't make any difference. The Johnson & Johnson vaccine, it's right now undergoing the FDA review, and it will probably be given EUA in the next 2 to 3 weeks. And the advantage of the Johnson & Johnson vaccine is that you only need to receive 1 dose. So it'll be convenient for you. You don't have to go back. You don't have to plan your schedule and such, so that you have to go back and get the second dose. It's not as effective as the Pfizer vaccine, but again, if you compare just one to one against the other, actually the Johnson vaccine is more effective, because the messenger RNA vaccines, after 1 dose, it's only about 50 plus or so effective. So it requires 2 doses to get to the 90%, over 90% protective or if efficacy. And so in a way, Johnson & Johnson vaccine is a little more protective.
There was a question about the messenger RNA vaccine. There's still a deep mystery at the root of the mRNA vaccine. How does the body recognize that the spike protein manufactured by our own cells is a foreign entity? Where is the catalog of non-foreign proteins?
Yeah, so the body, there's a whole bunch of these receptors, both on the surface of the cells, mammalian cells, and inside the cells. and they're called pattern recognition receptors. Sometimes they recognize like microbes, and there are other times they recognize tumor antigens. When a cell becomes cancerous, they recognize tumor antigens. And so whenever these receptors recognize these uh, 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 products that are considered to be foreign, it induces this inflammatory cascade. And so when the messenger RNA goes in, if it's a pure, clean messenger RNA with some of the nucleosides that have been altered, then it doesn't get recognized by these receptors. So the inflammation is not induced. And then as the amino acid gets pumped, then they're recognized as just part of the normal part of the cell, because they're just amino acids that are synthesized by these messenger RNA. And these messenger RNA uses these host cells' own machinery to translate the nucleosides into amino acids and then the protein. So there may be some recognition of that as foreign, and that way you might see some fever like we've been seeing, but that's not a prominent feature of the recognition of the protein as foreign.
Another question about effectiveness. In stating percentage of exposed to asymptomatic infection is 30 to 40%, how are you defining exposure, as that can vary by intensity?
Sure. So, that would vary from people to people. Since if someone is asymptomatic, that person is not going to get tested. And so, it's really difficult to study those populations, how much virus they're really shedding. There are some studies that have been done in these people, so-called the pre-symptomatic period. So these are people who are asymptomatic, but they eventually go on to become symptomatic. And these are usually done on close contacts of someone who had overt COVID-19. So if you follow those people, then you can sort of get an idea of how much virus is shed, and then get an idea of how much how much shedding is needed to transmit. And so, but I don't really have any information about detailed information about how many virus particles are really required to cause an effective transmission. Now, one other sort of maybe the related issue, the question is, can these vaccines that we now have protect against asymptomatic infection? And that we don't know yet. We should get some information soon. The Moderna vaccine, the Moderna people claim that their vaccine can prevent asymptomatic infection, not completely, but to a certain level. The Pfizer vaccine, they haven't come up with any particular statement yet, but we'll get that information shortly. And this is very important, right, for the vaccine to protect against asymptomatic infection, because there are two important features to all vaccines. One is to, of course, prevent the disease and severe disease and death in the individual who receives the vaccine. But the other important feature of a vaccine is to establish what's called herd immunity. And in order to establish herd immunity, you have to protect against asymptomatic infection. And so that's something that everybody's really waiting to hear about with these vaccines that we have.
Another question here. Encroachment of man upon animal environments may lead to more such pandemics. So is there a correlation between pandemic risks and poor environmental stewardship?
Oh, I think so. This is not the first time when we had this pandemic, when people encroaching parts of nature that we shouldn't be going into. The original SARS epidemic, the SARS-CoV-1, presumably started because of this practice of eating civet as a type of aphrodisiac in certain parts of China, and so that started this epidemic. The Ebola is another example in Africa, where the virus is in certain uh, um, animal reservoir, and then people encroach upon those reservoirs, and the virus gets transmitted from person to person in humans. So there are many examples like this, and it's probably this is I'm not a religious person, but this is a sort of a nature's way of maybe getting back at us. They're telling us not just leave us alone. Just stay, uh, in your own on side of the line, and because if you do, then you're gonna get burned. Uh,
Well,
so.
between the pandemic and climate change, there's a lot of arguments for vegetarianism, but that's another topic. Let's see. In Mexico, where our wonderful manager is, the Russian vaccine is what's being given.
Mhm.
Any reaction to that? You mentioned briefly.
Sure. So as I mentioned, the Russian vaccine is really very similar to the Johnson and Johnson vaccine. They use the adenovirus 26 to deliver the spike protein. And uh, the unfortunate thing about the Russian vaccine is they don't publish anything on efficacy and side effects and things like that. So we don't really have a good idea. I wish they had done that because they actually started the vaccination, to roll out the vaccine way before the U.S. And so they should have a lot of data, but we haven't heard anything as far as I mean, I haven't heard of any efficacy studies or there's some anecdotal information about the efficacy, and they claim that they're more than 90% effective, but I haven't heard anything about side effects and things like that. So, but if it works the same way as Johnson and Johnson vaccine, then I think it should be safe and it should be effective.
Let's see. How does a virus attenuate itself? Is this what happened to the SARS virus?
Mm-hmm.
What is the chance that the current COVID virus may attenuate itself within a year or two?
Yeah, so no one really knows exactly how viruses attenuate themselves, and since the original SARS coronavirus disappeared after 6 months, we don't really have that many strains to know what changes contributed to their disappearance. Um, when this current pandemic started, I sort of initially thought that this will also disappear like this first SARS coronavirus, and I was completely wrong. Um, and one of the reasons, and this is something that's not many people talk about. So as I mentioned early on, people thought that this virus wasn't undergoing mutation as rapidly as the first one, and certainly, and that was true. In fact, the mutation rate of this coronavirus was about 10 times slower than the mutation rate of viruses like the influenza virus or the Middle Eastern respiratory coronavirus. And that was the case for a while. And then sometime probably around April or so, we started seeing these mutants pop up in different places, starting in Europe. In Europe, they actually started even as early as late February. And then when we looked at the sequence, we noticed that there was some mutations occurring in what's called the RNA-dependent RNA polymerase, which is a gene, the enzyme that the virus used to string together the nucleosides. Okay, but it turns out that enzyme is also a very important what's called a proofreading enzyme. So these viruses they're tiny, but they're amazing. They actually have this enzyme that can correct the mistakes that they make when they start stringing along these nucleosides. Okay, and so this coronavirus had a very efficient proofreading enzyme, but sometime around late February, March, there was a mutation that occurred in that very gene that has the proofreading apparatus. And it's after that, then all these mutations started occurring. Okay, so the very enzyme needed to correct these mutations underwent mutation. So that's why now we're seeing more mutations than we had early on. And so the question is, are these mutations, beneficial for us or beneficial for the virus? Viruses are there. They don't mean to kill us. They're just their entire purpose of being a virus is to be a virus. Okay, to replicate themselves.
They're doing
and
it.
uh, and so they can mutate themselves out of existence, or they can become more virulent, or they can become more transmissible. These are all stochastic consequences, and so who knows what's going to happen. But as I mentioned, it's half jest. Humans have really contributed to some of these mutations because the more people who get infected, the more stressful it is for the virus. So they have to undergo mutations.
Interesting.
Okay, and so the greater the number of people get infected, more likely these mutations will occur.
A couple of questions about obtaining vaccines. So, are there diseases that people would have that would make getting the vaccine contraindicated, such as Lyme disease or lupus?
No, there's no contraindication for any of these vaccines. Or I should say the messenger RNA vaccines, because as I said, there's no infectious agent associated with this vaccine. But for the adenovirus vector, uh, virus vector vaccine, that might be an issue. So adenoviruses have been actually used for many, many years for all kinds of other medical purposes, such as gene therapy.
Mhm.
And there were some cases where they used the adenovirus to deliver some DNA and in some immunosuppressed individuals, and it caused a death in some of those people. So, but you have to be severely immunocompromised to probably develop that kind of adverse outcome. But that is something that people do need to watch out for. If you have any sort of underlying medical condition, it's probably safer to get the messenger RNA vaccine than the adenovirus vector, or they wait until the Novavax vaccine comes out, the protein. I wouldn't wait. I shouldn't say you should wait, but
Well, and then
if
there was, along those lines, a question of would it be dangerous to take the Johnson and Johnson vaccine first, and then many months later take one of the messenger RNA vaccines?
so, if you get the Johnson and Johnson vaccine, you only need to get it once. It's just a one dose vaccine. So you don't really need another vaccine after. Now, if it's the other way, if you take the messenger RNA vaccine first, and then can you then get the Johnson and Johnson vaccine? That's probably okay, but it's probably better to get the same messenger RNA vaccine, for your second dose.
You alluded to something at the end about will these vaccines be something like the flu shots? Should we anticipate that in a year or every other year that we will be needing to get a COVID shot like we should get a flu shot?
Yeah, at this point, we can't really say. Let's see what happens with these variants that are emerging in different parts of the world. We already know that the Novavax vaccine is only about 50% effective in South Africa because of that variant that's spread. Um, yeah, I'm not sure if that variant, if it entered, we've seen those. We've seen that variant from South Africa in a couple of states in the U.S. already. Um, and then we definitely have seen the UK variant in many states already. We're not sure if they'll start taking off like they did in those countries, but if they do, we may have to come up with a slightly modified versions of these vaccines. Um, and how often this has to be done, it would depend on how quickly these variants emerge, and whether or not these variants indeed are more transmissible and more deadly. Um, we really can't say. I'm somewhat optimistic. I think a lot of these reports about increased transmissibility and higher mortality are somewhat misleading because they don't take into some of the uh, epidemiologic considerations. For instance, if there was a variant that was reported here in Northern California, Santa Clara County, right? And people thought this was highly transmissible, but it turns out it was actually identified in an outbreak in San Jose in a Kaiser hospital. So you had these many cases of the infection due to the single strain, just happened to be a variant, but it was an outbreak. And so, of course, if it's an outbreak, you're going to see if it's more transmissible, but it's not. It wasn't more transmissible. It just happened to be an outbreak. So, and they happened to collect all these isolates, and they happened to undergo sequencing. So we have this mutation, this variant that they reported to be overly represented. It's not because they were transmissible. So they need to get that kind of information in South Africa and the UK. Maybe this mutant entered into a population where there weren't very many cases to begin with, And so that one just took off like wildfire in this virgin territory. And that may be why we're seeing this high mutation or the transmissibility. And I could be wrong, but my feeling is that these mutants may not spread like wildfire in the US. But there may be other variants that could spread like wildfire in the US. So we just don't know right now. I've been burned so many times by predictions that I'm not going to make any more predictions.
Question about if you've had both of your COVID vaccines, is there any reason to hold off on other kinds of shots like a flu shot or a shingles vaccine? And if so, for how long?
Yeah, so CDC does recommend to wait on the other shots. I can't remember exactly what they said. I think maybe 2 weeks or a month. And certainly they specifically made this recommendation for the influenza vaccine and the shingles vaccine.
Okay. And then question about the duration of the protection. Do we know at this point for how long?
Yeah, we don't really know. The messenger RNA vaccines, they induce really high titers of antibodies. And just comparing the antibody titers that people acquire from natural infections to what the vaccine can do, the 2 doses of the vaccine can induce an antibody response that's higher than some of the natural infections. And we know that with natural infections, so far they've shown that you can be protected up to 8 months. And of course, I'm talking about symptomatic infections. If you had an asymptomatic infection, the protective immunity may last maybe shorter. So if the vaccine can induce a very high titer, certainly more than 8 months, but we'll have to see.
Mm-hmm. Sort of moving more into the post-vaccine questions. So once you've received both of your vaccines, what guidelines would you give for then going back to, say, some normal activities, such as meeting indoors with people
Right.
who may not have been vaccinated?
Yeah. No, unfortunately, you need to continue to maintain all of the recommendations about social distancing and wearing masks that have been recommended up to this point. As I mentioned, right now we don't really know for sure that the vaccine can prevent asymptomatic infections. And so even if you were vaccinated, it's potentially, possible that you could still be asymptomatically infected and then transmit the infection to others, close contacts. And so until that's made clear, we need to be really taking in all the precautions that have been recommended by the public health services.
Continuing with social distancing and mask wearing and the rest.
Right.
So from your standpoint as an epidemiologist, when would you venture to say the pandemic would be over? What would be the statistics that would be needed to reach that point?
So I think the major probably statistic we need is the level of herd immunity that we can achieve. And Dr. Fauci, I know him and is my hero. He predicts that we can achieve a good herd immunity, which means about 70 to 80% of the population getting vaccinated, probably by this fall, or maybe early winter. So that means, if everybody really makes an effort to get vaccinated, we can probably get to that point. And so again, whether we can get to that point or not is again really dependent on people. We have these people who don't believe in getting the vaccines, and if we have too many of those, then we may not be able to get to that point in a timely fashion. And so this is something that is all up to us. It's not the virus.
Right. We have some questions which may be a little bit outside of your purview, more guidelines that the city and the states are giving, but about current guidelines about travel, say, when should we feel comfortable to travel, say, within California, or possibly even getting on a plane?
Mm-hmm.
to go further away?
Yeah, I would, watch out for what CDC says. Uh, the most recent recommendation from CDC is to minimize travel, non-essential travel, and so I would stick to that until CDC makes further recommendations.
It's a question about the rate of production of the messenger RNA vaccines in the US. Is this
Uh, yeah, that's a good question. I really don't know. You know, Pfizer is a much bigger company than Moderna, and so they're probably much faster in making more doses of the vaccine. But I really don't know what the rate of production is. So,
well, and we already know one of the big news items this last week was about the shortage of the
right,
vaccines in Europe
right. Yeah, Europe is having all kinds of issues right now. Yeah.
and the nationalism of the vaccines being a
Right, right,
real
right,
problem.
right.
So,
But
uh,
as I mentioned, the Johnson Johnson vaccine will probably be coming out soon, and then shortly after that, the Novavax vaccine. So, we're going to have several vaccines in the pipeline, and that will probably lessen this concern of shortages. If you're really concerned, you can always get the vaccines from China and Russia. And so, I have a daughter who was in Italy when this whole thing started, and she came back, and this was a program in Bologna where people from all over the world come. And when she came home, she was talking to some of her Chinese friends that she met, and they were back in China. And these Chinese friends were really surprised that we still hadn't gotten the vaccine, because China had already started the vaccine long before we started. So,
we're definitely behind for sure.
mhm.
Question about testing. If you take the test and it shows that you have antibodies, does that mean you won't catch it again, or should you still try to get the vaccine?
Yeah, you should still go ahead and get the vaccine because your protection really would depend on the level, the titer of the antibody. And so, as I mentioned, uh, um, if you have a high enough antibody from the natural infection, you're probably protected. Um, and so, you may not have to get the vaccine right away, but you should get the vaccine at some point. Now, there's some reports of uh, uh, people who get the first vaccine, first dose, and then shortly after that, they actually get infected with the virus. And and it's happened during the clinical trials as well. And it happened to one of my former students. She got the vaccine, and then a couple of days later, she started developing respiratory symptoms, and she indeed ended up getting infected. So she got infected before the vaccine had induced its effect. And it takes about 2 weeks after the vaccination for your body to mount an immune response that's protective. And so, so she was told to wait 3 months before she gets her second dose of the vaccine.
Interesting. Okay. There have been a couple of questions about understanding the concept of herd immunity. Um, let's see. Some people take it to mean everyone else is vaccinated, so that means I don't have to. Or what do immunologists mean by herd immunity?
So there is a specific formula you can use to calculate herd immunity. So it depends on the what's called the reproductive number. The number of people that infected person can infect. And so if the number is more than one, then the epidemic will continue. If the number falls below one, then the epidemic will eventually end, just finish. And so use that number to figure out the herd immunity. And so um, and it really depends on the virus. For instance, a highly transmissible virus like the measles virus, you need more than 90% of the population to be vaccinated. For influenza, you need about 70%. And so, from what we know about this coronavirus, you need about 70 to 80% of the population to be vaccinated to interrupt further transmission, meaning that the reproductive number is kept at less than one.
Yeah. So, considering some years in the future, how might you anticipate that COVID vaccines could be worked into a routine vaccination schedule? Similarly, would booster shots be inoculated anew be required periodically?
So, if the virus evolves to become like the influenza virus, yes, that's probably what we're going to have to end up doing.
Mhm.
And then the other question is, okay, so if we clearly don't see any major adverse events associated with the messenger RNA vaccine, then this technology could be applied to all the other vaccines that we now use, such as the influenza vaccine, such as the measles vaccine, all of the childhood vaccines. Everything could be done by messenger RNA technology. And we'll see if this happens. If this happens, then that person I mentioned, Dr. Kariko, will probably get a Nobel Prize together with Dr. Drew Weissman.
Right. Very exciting
Yeah.
prospect.
Mhm.
Um, so final questions about um, the differential impact on people of color
Mhm.
and areas of, say, lower populations with lower standards of living. I know that's, Leah, this is in other work that you'd done previously was something that you were studying. Any comments you want to make or speculation about why those populations have been more vulnerable and what
Mhm.
we can do to both boost their immunity and their willingness to get vaccinated?
Sure. And so, we've been hearing about the disparity, especially in terms of the adverse outcomes and deaths among people of color in this country, especially in California. And and there are all kinds of reasons, of course. There are sociological, access to healthcare services, delayed diagnosis, delayed testing, et cetera, et cetera. Those are all true. But one thing that not many people talk about is a sort of the biology of this epidemic. Um, there are many people of color who actually die without having any sort of underlying medical conditions, without having any other um, sociological links. Um, um, and so that's the area that I'm interested in. Why is it that uh, people of color have increased have a disproportionate higher number of deaths and hospitalization rates. And we think it has to do with how the virus is transmitted. And it's directly linked to the type of occupations that these people are mostly involved in. These people are, many of them are not able to work from home. So they have to go out. They are often in types of work that makes it very uncomfortable for them to wear masks. They're not intentionally not wearing masks. They're just I mean, this. When you exert yourself wearing masks, it's very difficult to keep them on. When we go hiking or you go running, it's very difficult to keep masks on. So many of these people are involved in types of work conditions where it's very difficult to really keep socially distant. And so when you are in that kind of situation, you're very likely to be reinfected with the virus. And there's a phenomena in other types of viral illnesses called antibody-dependent enhancement, where you get reinfected with a different strain of the same virus. It induces this aberrant inflammatory response that can lead to death. This happens in little kids with dengue. In places like Brazil and India where they have dengue, there are four types of dengue virus. If you get infected with one, if you get infected with the same strain later, you're protected. But if you get infected with a different strain, it can induce this phenomena that can cause really severe outbreaks. As I mentioned, I showed you that graph. We have multiple variants circulating at once in California, all over the world. And so in these types of professions, you're constantly exposed to other people, especially if your first infection is asymptomatic, you're not going to change your behavior, right? You're not going to start protecting yourself. And if you get infected again and they get the symptoms, that might look like it was your first infection, but indeed it is probably a second infection. And if you're getting a second infection, you're more likely to get severe disease.
Interesting.
And we've actually seen case reports of this where they've actually documented clear second infection with a different strain of the virus. And there were at least four such reports in the US. And three of those people had really bad outcomes. And they were young people. They were young, healthy adults who got these infections. And so the reinfection rate, I think, is happening much more frequently than we think, and in these populations that have certain types of occupations. And so part of the vaccine rollout plan includes people like that. They're included in phase one. One, I think 1B tier 2. It's a very complicated tier system. And so tier 2, phase 1B includes people who are in that type of occupation, those types of occupation. Mm-hmm. And so they are being targeted for or prioritized for vaccination. So that's a good response.
That's good. May not be enough soon enough, but at least that's something. So, right. Before I finish this off and thank you, I just wanted to dedicate this wonderful presentation to two people. One was the first fatality in Oakland, a woman named Barbara Hopper, who was a friend of mine, a realtor, wonderful Black woman and a pillar in our community. And also to Dr. Kopilov, Araceli's father, who, again, a pillar in his community and succumbed. So our thoughts are with you.
Yes.
Thank you so much, Lee, for giving so much. We're getting terrific comments about.
Thank you. Thank you. It was a real pleasure. Thank you, Arlene, again.
For the first time, and lots of great information. Thank you for being with us. Thank you all for being here on this rainy night and not having to go out in the rain to get this great presentation. I hope you will come back.
Sure, I'll be happy to. Mm-hmm.
And to all of you on different topics, I hope you'll come back. We'll be here the first Mondays of most months. Again, on topics of hope, we're going to be doing something, say, for Earth Day, of how we can contribute to making our world a better place. And this was our medical tribute. Last month was our musical tribute to how musicians have adapted to this pandemic and done some creative and wonderful reactions. I'll just mention, for those of you who were here last time or listened to the presentation, one of our groups was Emma's Revolution. They're emmasrevolution.com. And they very quickly reacted. January 6th, they came out with a new song that day in January in reaction to the atrocities. And just yesterday, I learned a new song from them, which was setting to music the last stanza of the wonderful poem that our new hero, Amanda Gorman, our youth poet laureate, inspired all of us with. See the light, be the light. So with those words, I urge you all to be the light and let it shine through all your communities. Thank you for being here. Thank you, Lee, Dr.
Thank you. Thank you for listening.
Thank you.
Bye.